All right, welcome back, everybody. So today, what we're going to be talking about is regression adjustment, and this is going to be the last topic of the class. And I'm going to bring a very causal inference approach to regression. Of course, regression does not necessarily need to be causal, but I think that in practice, you're going to be dealing with things like confounding when you submit papers and responding to reviewers about why you included some confounders and why you didn't include other confounders. So, a lot of today is going to be this idea of omitted variable bias. So, omitted variable bias, variable bias. Okay. Um, And so, just to remind you, this omitted variable bias is really related to a concept that we talked about before of confounding or confoundedness. Remember the methods that we talked about last week, is particularly inverse propensity treatment weighting, uh, assumed that we were in a situation of unconfoundedness. Um, Now we're going to continue to make that assumption, and we're just going to give a new name to the bias that could result called omitted variable bias. So let's just do a little bit of review of kind of the fundamentals of causal inference here. So the first thing we said that any causal effect, a causal effect is simply a comparison of potential outcomes, all right? So if we were looking at the causal effect of HPV vaccines on developing cervical lesions later in life, ideally for each individual, we would know whether or not they had lesions if given the vaccine, or whether or not they had, and we would want to know whether or not they got lesions if not administered the vaccine. And so ideally, we'd want to know the situation and we would want to know the outcome in both settings, but we couldn't actually do that. We can't actually see both potential outcomes at the same time. So if we gave the HPV vaccine to an individual, we could only see the Y1 potential outcome. We could not see the Y0 potential outcome. Similarly, if someone did not have the HPV vaccine, we would only in that case be able to see the Y0 vaccine, but not the Y1. So this led us to this idea that we're not going to ever really know an individual causal effect, but hopefully what I can estimate is an average causal effect, so an average treatment effect, right? So if I were to take the population average of these, so that E is that average, and then we have Y0, then we might want to flip y1 and y0, but nonetheless, I can't estimate an individual causal effect, so hopefully I can take an average, I can estimate an average treatment effect. And and the thing here is that not only do we want to just estimate the average treatment effect, we want to be able to do it just on data that we actually observe. And so for this individual, we just see the y1s. So we might just say, like, I'm going to just take the y1s of those that I observe. So I'm going to take the mean y1 that I observe for those that were given treatment. If given treatment, and I'm going to subtract the mean of y zeros, if not given treatment. Not, not given treatment. Okay, so I'm just taking the y's that were given treatment, subtracting from the y's that were not given treatment, and hopefully that estimate is a good estimate of the average treatment effect, even though I don't see it for each individual. And we said we could do that well if exchangeability held. So remember, exchangeability was this idea that our potential outcomes are apples to apples in both treatment groups. So y0, y1 given is independent of the treatment assignment A. And so all that means is that if you were to give treatment to those who were controlled, their y1s would be the same, and so on and so forth. So um, the hour two, we said, okay, well, in observational studies and RCTs, this makes sense because RCTs balance everything. Everything's apples to apples in RCTs. That's the beauty of randomizing this treatment assignment. But in observational studies, we may not be able to make this claim that we have um, exchangeability, right? And we say, well, maybe we can get closer to exchangeability if instead what I do is I look inside particular strata. So I have y0, y1. We're going to say that this is going to be independent of A given X. All right, so I'm going to look in each strata, whether that's, for example, in the vitamin supplement group, whether we're looking at health conscious individuals or exercise. But basically, I'm going to slice and dice my data to find groups who are similar enough to each other so that we can make a more effective argument that they're exchangeable in Y0 and Y1 within that strata. And we said, well, this is better. So now we're kind of happy. Except the only problem is that we could have lots and lots of X's here, and so it's really hard to find, for example, a matched control. So one thing we saw, and this was proven by Rosenbaum and Rubin, was that we don't actually have to um, create strata of, if I'm controlling for, 20 different variables, I don't need to create thousands and thousands of strata. What I can instead do is just worry about balancing with respect to the propensity score, right? So E of X. All right, and so this propensity score was nice because it's just a one number summary. So one number. And if I were to just look and I were to divvy up observations with similar propensity scores, then hopefully I'm in a good position to make the claim that y0 and y1 are exchangeable. Okay, and if they're exchangeable, then I'm in a good position to say that the effect that we're estimating is in fact a causal effect. Okay, so this required unconfoundedness. So what we did here is we said that this required unconfoundedness, right? Unconfoundedness. Unconfoundedness. So ideally, we would want to be able to compare the y zeros and y ones to everybody, right? Like if we could show that y0 and y ones are apples to apples in the treatment and the control group, then we could be assured that we have a causal effect. But we can never do that because we can never see both potential outcomes for an individual. So instead of looking at y0 and y1, what I'm going to look at is instead whether or not I have covariant balance, right? So that the covariates are apples to apples. It doesn't matter if I look at the treatment or the control group, they have similar levels of education, similar levels of income, similar triglyceride levels, whatever it is that we're trying to measure. We want to see that those things are balanced, right, on things that we can actually observe. And so, why was balance important? Well, balance is important because, ideally we would want to show balance on the y zeros and y ones, but I can't do that. So I'm going to look at what I can't do that. So I'm going to look at everything that determines y1 that I can and hope for balance here, even though I can't get balance on the y's. Of course, we are always under this threat that there are some variables that we can't actually observe. And so, what are those variables? Well, those variables can be confounding variables. And if we have imbalance on these confounding variables that I don't actually observe, then we're not really set up well to make an argument that we have exchangeability, and then our causal argument breaks down. So that was the high level thing that we want to look at balance on the actual observed covariates. Let's go ahead and just kind of remind ourselves one of the ways that we can get at balance. So one of the ways that we can get at balance is through inverse propensity treatment weights. And so what does that mean? Well, what it means is that I'm going to calculate a propensity score, or in other words, I'm going to find the probability of a person being assigned given to treatment given their background covariates, and then I'm going to reweight them. Okay, so then I'm going to reweight them. So let's go ahead and let's just take, for example, a new example that we're going to do, which is the come on, the NHEFS smoking cessation study. So this was conducted between 1971 and 1982. And the outcome here was the change in BMI, and our treatment was whether or not individuals quit smoking. Now, I stratified it to just include males who were 23 to 35 years old and who survived to at least 1982. So they're 25 to 35 years old in 1971, and they survived to at least 1982. And so I want to know the question that's going to be guiding this is does quitting smoking change BMI, right? So one of the arguments has been that if you quit smoking, that causes an increase in your BMI. Instead of smoking, you start eating and overeating, and so let's go ahead and take a look at that. So I'm going to use a few different confounding variables here. So the one is comorbidities. So I have baseline BMI, the cholesterol, diabetes, and whether or not they've been diagnosed with high blood pressure. I'm going to look at their lifestyle variables, so how frequently they exercise and how frequently they consume alcohol. And then also I have their age, education, race, and marital status. So these are going to be the variables that I want to make sure um, that I have balance between those who quit and those who didn't quit in order to be in a good assumption that there's a causal effect. Okay. So what is inverse propensity treatment weighting? Okay, so let me just kind of walk you through this. So I have these comorbidities, these lifestyle variables, and these demographics, and I'm going to run a prediction model of whether or not that individual quit smoking. And from that, I can get a probability value. And we're going to call that probability value the propensity score. So it's the propensity score of X, so E of X. And so I'm going to reweight individuals based on that E of X. So if I have a treated individual, I'm just going to take the reciprocal of their propensity score. And if I have a control individual, I'm going to take the reciprocal of 1 minus their propensity score. So you might ask yourself, well, why this? And the reason is that for those who have for those with for those with a for the treated group, what we're going to do is we're going to downweight. Oh, that didn't work. Let me just do this. We are going to, here we go. Let me make this smaller. We're going to, for the treated group, we are going to downweight individuals with a large probability of assignment. Right? So obviously we know either an individual is getting assigned or they're not getting assigned, but we can create a probability of their assignment. Well, with smoking, they're not. They either someone's quit smokes or they don't quit smoking, but we can get a probability of whether or not they quit smoking. We're going to downweight for those who did quit smoking, those who have a large probability of quitting smoking. And conversely, we're going to upweight individuals with a small probability of quitting smoking. Quitting, quitting smoking. Okay, and so by downweighting individuals who did quit smoking, um, and who had a high chance of quitting smoking, and by upweighting those um, who didn't quit smoking, um, we are we are effectively making them more apples to apples. Okay. In fact, we can see this. Let me do this. Okay. So here's the propensity treatment weight. We can see these are those who continue to smoke. So that's A is equal to 0. And these are the people who smoke. So A is equal to 1. And we can see that those who continue to smoke had a lower probability on average of quitting smoking than those who did uh, quit smoking. They had a higher probability on average given their comorbidities, lifestyle, and demographics. Okay. And so what I'm going to do is I'm going to do this inverse propensity treatment weighting. And so for those who continue to smoke, A is equal to 0, I'm going to really upweight this guy here, right? They're going to have a much larger impact on the causal effect than, say, somebody who's down here. And conversely, for the quit smoke group, I'm going to upweight somebody who's over here and downweight those who have a high probability of actually smoking. And so what that's going to do, that reweighting, is going to create a distribution that starts to look much closer to each other. So you can see the boxes are kind of misaligned here, and now the interquartile range is that's what the boxes is. So it's like the 75th to 25th percentile, basically match each other. Okay, and so, what we're hoping to do with this propensity treatment weight is to go from the situation where we have large imbalance, right? So, this was before inverse propensity treatment weight. We can see that there's big differences in education between those who quit and those who don't quit, big differences in marital status, big differences in age. High blood pressure, so on and so forth. Less differences in terms of exercise frequency or diabetes or baseline BMI. But nonetheless, we have this imbalanced situation that's predicting whether or not someone actually, whether or not somebody actually quits smoking. And we're going to want to come to a situation where we actually take this education once we reweight individuals, that the imbalance that we observe actually is much smaller, that we have more of an apples to apples comparison with regards to education, marital status, age, so on and so forth. So here's the plot after doing inverse propensity treatment weighting. And you can see that it did reduce the imbalance, although it didn't completely resolve it. So if this is a real analysis, that would still be concerning, but for pedagogical purposes, we'll continue. It did resolve the imbalance with age, for example. So we can see that it did reduce the amount of imbalance just by reweighting observations, upweighting and downweighting the observations according to those inverse propensity treatment weights. So that looks good, but we need to be careful of one thing, and that thing is that we can only balance on variables that are included in the propensity score model. So for example, if I go back up here and I were to look at my model, let's say I were to just balance on comorbidities and I were to ignore lifestyle and demographics, well, then I would be able to balance on my comorbidities would be balanced. so I'm going to create a propensity score model that only includes comorbidities, then my comorbidities will show greater balance, but lifestyle and demographics won't. And similarly, let's say I were to balance on, or I were to create a propensity score model on comorbidities and lifestyle, but not on demographics. Well, then I would be balanced on comorbidities and lifestyle, but not. I won't have balance on the demographics, and we can see this in the next plot. So if I were to balance only on comorbidities, we can see that the comorbidities have decreased, but there's still balance in alcohol frequency. That large balance in terms of age, marital status, and years of schooling is still there. Similarly, if I were to now include lifestyle, we can see that the imbalance in alcohol frequency has decreased, but I still have imbalance on the actual demographic variables itself. So we can only balance on those that are actually included when predicting the probability of assignment. So you may be wondering to yourself, well, what is the causal effect? Or at least the estimated causal effect with the best that I can do with the covariates that I have here, the confounders that I have here. If we were to just look naively, so in other words, we're not controlling for anything, we're not adjusting for comorbidities or lifestyle or demographics, you can see that it leads to a 1.5 percentage increase in the BMI. With comorbidities, we can see that quitting smoking seems to lead to a 1.8 increase. When I start adjusting for more confounders, it gets even stronger, right? So quitting smoking after adjusting for these confounders seems to have this causal effect on BMI changes, on increasing BMI. Now, we got to be careful with this. This does not mean smoking is good for you, nor have I ruled out other potential confounders that could complicate this relationship because I didn't randomize quitting smoking. But nonetheless, with the covariates, the confounders that I do have, it appears that there may be a causal effect between quitting smoking and increasing an individual's BMI. I'm sure other people have actually done causal studies, stronger causal studies than this pedagogical example, but nonetheless, this is what I'm seeing with just this data set and these covariates. Okay, so not a publishable quality analysis, but nonetheless something useful for us to understand these concepts. Okay, um, so keep this, 1.5 to 2.21 in the back of your mind as we start talking about another way that we can adjust for potential confounders. And this way, we're going to title as regression adjustment. All right. And so regression adjustment, you can think of it, if you're not familiar, is you can think of it as like a best fit line. Okay. So I'll have my outcome. So my outcome is BMI change. And I will predict that outcome based on a covariate. So the most simple covariate could just be quitting smoking. So does the BMI change? Is that predicted by quitting smoking? Just to give you an intuition of like this best fit line um, uh, framing, let's say we wanted to predict BMI in 1982. So in this case, my Y is BMI in 1982. And my X is going to be my BMI in 1972. And so we can see that your BMI in 1972 does seem to predict what your BMI is going to be in 1982. In fact, there's a strong positive correlation. So correlation can go from -1 to 1. So we can have a correlation, and that can go from -1 to 1. A correlation of 1 would be a perfect linear relationship. So the dots would exactly fall on this line. Similarly, so here's my perfect core, r is equal to 1. Oh, that should be right on that line. Okay. And that's r is equal to 1. Alternatively, we could have a perfect negative correlation, r equal to -1. And so this would fall on a line perfectly. So pretend like that goes over through. It's kind of hard to write on a computer with a pen. I'm not very good at it, but I'm trying. So the critical thing here is that R is measuring how well how well points fall on a perfect line, on a line, okay? And so we have 0.884, which means that we have some deviation from it, but we can definitely see this upward trend, and we call that a positive association. So higher BMI in 1971 is associated with a higher BMI in 1982. In fact, if we were going to make a model out of it, we would say that, and we were to fit it in software, we would get that beta 1 is 0.95. So I fit this in software. So what that means is that I have y, so my BMI in 1982 is equal to some intercept value. So it's some number plus 0.95 times my BMI in 1972. So I'll just call that X. And what does that mean? What that means, and this might take you back a little bit, but what that means is that a 1 unit, a 1 unit difference in BMI in 1971 is associated with a 0.95 unit BMI in 1982, right? So 1 unit increase in BMI in 1971, or 1% increase in BMI in 1971, is associated with a 0.95 increase in 1972. So it's just, if this is just a slope, right? So this is a slope. All right, so this might have been a while ago, but you probably did like mx plus b in high school for a linear line. This slope is often what we are estimating. That's my regression coefficient. And what it just means is that a 1 unit increase in x changes y by this slope amount. Okay. All right. So that was a positive correlation. Let's go ahead and look at a negative correlation. So let's just look at the change in BMI. So the change in BMI between 1982 and 1971. And we can see that there seems to be, if we were to predict the change in BMI based on their BMI in 1971, we can see that an increased BMI, so if you have a larger BMI in 1971, that's going to predict a lower change in BMI in 1982. In other words, that would be something like less weight gain. Hopefully weight loss, but for this to be weight loss, this number would have to be negative, but overall less weight actual gain. Okay, and so we can see that this isn't as strong of a relationship. The lines tend to be pretty spaced apart from the dots tend to be pretty spaced apart from this actual line. So we call this a weak negative association. And in fact, you can see it's much closer to 0 than the one that was before. And if I were to put this in software and get a regression coefficient or slope of this line, I would see that, so I'm going to make that triangle. Ooh, there we go. So a 1 unit, a 1 unit, a 1 unit change in BMI in 1971 is associated with a decrease of 0.053 percentage point change in BMI. Okay. So that's at a high level. All we're doing with regression is estimating slopes of linear lines. And of course, we could, and why it's useful is that we could actually predict y with lots of different covariates. So it's not just one covariate that we can do. That would be simple linear regression. But in fact, we can do lots of different covariates. Like we could predict change in BMI based on whether or not, based on their sex, based on their BMI from 1971, based on whether or not they took a weight loss pill, all these other things. Okay, and why would we want to do that? Well, these can be confounders in our model, and so each of these B's represent of holding the other effects constant, right? So if our goal is to look at a change in BMI, so y is my change in BMI, and I were to look at, so this is change in BMI, and I want to know what the effect is of, so I'll have some intercept, and I'll have my beta 1, and we're going to say my treatment assignment is quitting smoking. Let's undo that. Quitting smoking, right? Well, I would want to control for a bunch of confounders, or basically look at A holding everything else constant. So that could be 2, and I could put in something like um, cholesterol or just comorbidities. Morbidities, I can put in B3, and I could put in things like lifestyle. I could put in other things like beta 4, and this would be things like demographics, right? So even though all I'm interested in is whether or not, so 1 unit change in quitting smoking would be whether or not you quit smoking or not. So if A is 1, that means you quit smoking. Then that means this beta 1 is telling me the average change in your BMI, or average change in BMI among those who quit smoking holding comorbidities, lifestyle, and demographics constant, right? So the key thing here is that we're holding constant. The typical languages is that we're holding constant all of these different controls, and so this is a much like going divvying up the data into individual strata, and looking at the change in BMI and whether or not quitting smoking whether or not we saw that quitting smoking uh, manifested in a change in BMI within the strata. This is doing that in just kind of a modeling relationship. Okay, and so that's what this is saying here. If we were to put this in a regression model, right? So the first thing I'm going to do is I'm going to look at the BMI change, and the only thing I'm going to control for is your baseline BMI and see whether or not quitting smoking is associated with an average change. And I see that that beta 1 is 1.53. So in other words, it seems like it's increasing. So those who quit smoking tend to have a larger BMI change than those who don't quit smoking on average, controlling for baseline BMI, right? So the interpretation is here is that after adjusting for baseline BMI, quitting smoking is associated with a 1.53 unit increase in BMI, right? So uh, when we adjusted using IPTW, we saw it was something like, I think, 2.2. So we saw even larger change with adjusting for um, all the other different types of confounders. And of course, we haven't actually adjusted for every single confounder at this point yet, but this is how this 1.53 would be interpreted. Okay, so what is it that we are actually doing here, just visually? what we're doing is so we have BMI in 1971, so that's my baseline BMI, and my outcome is my change in BMI. And all we're doing is we're creating different lines based on your smoking status. So this orangish one is those who did not quit, and this bluish one is those who did quit. And so what it's saying is that for both lines, it decreases, that line decreases by 1.53. So this is, here we go. Let me put this in. That the difference here, right here and here, everywhere we look, so holding constant BMI in 1971, if I were to look at it, it's 1.53. The difference in BMI is 1. Let me put this right here. So this is this difference. Let me actually make this bigger. And that's going to be way too big. Let's make this a obvious color. How about red? So no matter where I'm at, this difference is 1.53. So minus 1.53 is the difference, or another way to say that is going from those who did not quit, which is here, to those who did quit. That would be a positive 1.53. So I shouldn't say negative 0.153. I should say positive. Put it right here. And it's not working again. Now let's try. So this is plus 1.53. Okay. So holding constant BMI, we see a 1.53 unit increase in the change in BMI. Holding constant the BMI in 1971. Okay. So why not, instead of just adjusting for prime baseline BMI, why not adjust for all those other comorbidities like cholesterol and blood pressure and diabetes and lifestyle variables and demographics? And so that's what I did here, because I just wanted to compare the different outcomes. So if we were to just look at baseline, it's 1.53. If we were to now put in um, all these other comorbidities like cholesterol, diabetes, and high blood pressure, then our estimated difference is now 1.8 percentage point change in BMI. So it's going larger. And now the next one I'm going to do is put in the lifestyle variables. So my lifestyle variables were things like exercise, alcohol frequency, um, exercise and alcohol frequency, and so now it's gone all the way up to 1.887. And then the next one is something with demographics, so now it's gone up to 2, right? So that's much closer to the 2.2 that we saw with the inverse propensity treatment weight. So we're getting much closer to the estimate from the inverse propensity treatment weighting by controlling for all these different variables. Okay, so the critical thing here is that if I omit confounders, it appears like this one this true is different, right? This is 1.53 is definitely different than this 2.07 or this 2.2 that we saw above. And we're going to say that we don't trust this one as much because we're going to say that this is likely a biased estimate, right? So what do I mean by biased? Is that in the unconfounded situation, or in the situation where I'm most likely to be able to compare apples to apples based on their potential outcomes, this number, it doesn't make isn't a good approximation to the number that I get when I start controlling for those confounded situation for the confounders, and I'm in a better situation to argue that that we have that exchangeability, that conditional exchangeability, with the potential outcomes. So we would in fact say that this is negatively biased. So this estimate with just the baseline is negatively biased. And that just means that it's underestimating. Okay? It's underestimating the effect that we would get if we were to actually control for the actual confounder. It's underestimating the effect. Okay. So let's talk about, and this is an example critically of omitted variable bias. Okay. So we are omitting all of these other variables, and that's resulting to bias. Now, can we predict whether or not we are going to underestimate or overestimate an effect based on omitting a certain variable? And this is critical because when you're talking with reviewers, you want to be able to make a forecast of what would change if you were to insert one variable or another. And it turns out that you can actually um, you can predict whether or not you're going to over or underestimate the effect. Let me explain. So what we have quitting smoking, and we're hypothesizing that that causes um, an increase in your BMI, and then we have a bunch of confounders. Okay, so we have confounders, things that predict whether or not you quit smoking, and things that predict you um, whether or not you experience weight change. Okay, so let's say you were in the situation that there we go. You're in the situation that you seem to know that your confounder is going to um, positively predict your uh, whether or not you quit smoking. So it makes you more likely to quit smoking. So that would be positive. And let's say you're in the situation that your confounder is also going to predict whether or not you have weight gain. Okay. So maybe that's like having a child, right? It predicts that you're going to quit smoking, and having a child makes it harder to exercise, which will predict whether or not you increase your BMI. Just have less time. And so in this case, all I'm going to do is I'm going to multiply the signs, right? So this is a positive number, so we could just say like this is 1. This is like 1, and this is like 1 as well. So 1 times 1 is equal to 1. That's a positive number. And so that means that my bias is going to overestimate. So if I were to omit whether or not you have a child, my bias is going to be positive. So my causal effect in this case might be like, well, let's just say 2.2. But I have overestimated. So the truth, this is what I observe. But the truth, if I were to actually include having a child, it would be actually lower. So it'd be something like 1.3 because I've overestimated. My bias is positive because it's positive times positive is positive. Conversely, let me undo that. And let me get rid of this. Conversely, let's say that, so we have some kind of confounder where it positively predicts your treatment assignment, but it negatively predicts your BMI estimate, right? So this could be something like a weight loss drug. In this case, I'd have a positive times a negative. That's going to result. So positive times a negative is going to result in a negative. And so that means I'm going to underestimate. So if I observe 2.2, that means controlling for this confounder, like a weight loss drug, my truth might be closer to something like 2.5. All right, and so on and so forth. So all you have to do is just draw this z to a, the z to y, and then just kind of think through, just multiply, okay, is this a positive correlation or is this a negative correlation, and multiply these two things. That'll give you the sign of the bias. So that means that you've either overestimated or you've underestimated. So let's do a few more examples of this because we're going to be doing this in hour 2. A few more examples. Okay. So let's look at like exercise. So we had our A, so we have our Z, and our Z is going to be exercise. And this predicts A and Y. So it turns out that our exercise with the outcome, yeah, from the data we can see that it's a positive correlation. So obviously if you exercise, you're more likely to. Hmm, that's interesting. If you, I guess that's true. I, the, the more exercise, you should have a positive change in your weight gain. I don't think that that's actually true. But let's go with it. I'll double check that. But I think that that's actually, this should be negative. But nonetheless, it's saying that I have a positive correlation here. If I were to look at quitting smoking and exercise, so if you quit smoking, this seems to be a slightly negative association. So that's negative times positive is going to be a negative, which means that I have underestimated the effect. So in fact, yeah, so I had a 1.8, and now with exercise, that's an underestimate. So once I put exercise in, it's now 1.88, so slightly bigger. It's like zero point zero 0.08 larger because I've underestimated the effect. Let's go ahead and look. If I were to omit age, so here we have Z. Okay, whether or not you gain weight is negative or is positively associated with your age in 1971. So this is positive, and then this is negative. Let's see, if you were to quit, you're more likely to quit smoking. So this is positive. So Z to A. So that's my age. So the age with outcome is positive. And then the age with whether or not you quit smoking was also positive. So this is a positive, which means I've overestimated. Okay. And in fact, if you were to put age in, you would get something that would actually be lower. So it positively biased the treatment effect. Let's say I were to do baseline BMI. Okay, so baseline BMI. So again, we have this situation where I have Z, A, and Y. Okay, so it turns out that baseline BMI is negatively associated with outcome. We saw that before. So it's a weak negative association. And then the correlation between your BMI, your baseline BMI, and quitting smoking was positive. So you're more likely to quit smoking with if you have a higher initial BMI. So this would be a negative value. So you're underestimating. Okay. And so what does that mean? It means that your bias, your if you were to put it in, if you were to put BMI in, you would expect a bigger number, go from like 2.2 to 2.4, for example, in terms of the effect of A on Y. Okay. Okay. So that's omitted variable bias, and going through that exercise of drawing the Z, A's, and Y's, and putting out the signs and doing that multiplication will give you a sense of whether or not you're overestimating or underestimating the effect. And we're going to be doing lots of practice with that in the next hour. So the last thing, so that's regression adjustment. We see that with regression adjustment, we can get something that is much closer, something similar to the IPTW adjustment. So it seems like we have two ways of doing the same thing. The natural question is one better than the other. And what I would say is, I wouldn't think of it in terms of one being better than the other. They actually just make different assumptions. So one of the assumptions with regression adjustment is that you have a correct functional form. So remember, I said that it's a line, right? I said that you are assuming a linear relationship, so that you can draw a straight line and things would follow from it along that line. But what if you have a highly nonlinear relationship, right? Something like this. Um, well, unless you've perfectly matched that functional form, which can be hard to do, um, then your regression adjustment may be biased. And in fact, it would be biased if your sample is unbalanced with each other. Alternatively, if your propensity score model is misspecified, so again, with the propensity score model, you also have to make things like that line, that linearity assumption. And if that's misspecified, then your IPTW estimate, what you get from IPTW, from inverse propensity treatment weighting, could be biased as well. So the natural question is, well, can I just reweight my estimates and get a reasonable, a better estimate, a more robust estimate of the causal effect? So in other words, can I combine IPTW with regression? And the answer is you can absolutely do both. All right, there's no reason why you can't do both at the same time. This is called doubly robust. So very um, reassuring name of doubly robust, because either the propensity score model can have some type of misspecification, or the regression model can have some misspecification. You get two chances to essentially get it right. So here is what I'm doing. I'm actually going to um, fit four models. So one with no confounders, one with baseline BMI, one with comorbidities, and then one with all the confounders. That's lifestyle and demographics. And you can see that that the effect that I'm getting of quitting smoking is remaining pretty stable over the different estimates. So you might ask, well, why go through all this? Well, one thing you can notice here is that by including a regression model, so here I've combined the regression model with the propensity treatment weighting, you can see that by including the regression model, we're actually getting smaller standard errors. Okay, so that's good. It's increasing our power. So we do like that. That's one benefit. In addition to getting it, um, two ways of getting it right by combining inverse propensity treatment weighting and regression, you are also in a good position where you can actually increase your power. So that's called doubly robust estimation. In the next hour, right? So let me just kind of give an overview of what we've covered. Remember that in a randomized controlled trial, balance holds by randomization. And as a result of that, it turns out that you don't really have to worry about functional misspecifications, right? You can do a simple average, and you're going to get the right. You're not going to have a confounded situation. So it's highly robust, minimal model dependency. If you were to do an observational study with IAPTW, now you are making some assumptions, so you still have some kind of model dependence. But if you were to balance on the confounders, you have good balance, then you don't really have to worry about it not following a perfect linear relationship, or a relationship where you're assuming that it follows a straight line. Because the imbalance that would cause that to be an issue has been corrected for. So next hour, what we're going to do some activities where we focus solely on omitted variable bias, practice with omitted variable bias. because I just think that that is so critical when you respond to reviewers or when you start thinking about a study, for you to design studies well, and to effectively communicate with reviewers, because confounders come up all the time. And a knee-jerk reaction is that if you have confounders that you didn't think about or couldn't control for, that must mean that your conclusions are wrong. But the reviewer themselves haven't always thought about whether or not the direction of the bias is such that it would actually invalidate your conclusions, or whether or not you found an effect but that's just underestimated. And so if you had controlled for it, you would have an even larger effect, and you'd have happier news. So we're going to do some omitted variable bias practice in the next hour. Thank you guys so much, and I will see you on Thursday.